let's say we are, because we want to involve chemical energy here. Let's say we are creating, or we're trying to melt some ice by burning some fuel. Let's say we start with, let's say 3 kilograms of ice that's currently at -10 degrees Celsius. And we burn let's say we burn 10 moles of fuel X using the reaction X plus O2 combusts to XO2. So X in this case, let's just say is some hypothetical fuel. Maybe we don't even know what chemical it is, but we know it interacts with oxygen in a combustion reaction and creates this combustion product. And let's say as it does so, it releases energy. If it didn't release energy, of course, it wouldn't really be useful as a fuel. The thing is, as we're combusting it, we're really doing two things. The reagents are breaking apart. We start with some molecules that get shredded apart, so we're breaking bonds. And when you're breaking bonds, what happens to bond energy if you break bonds?
It increases?
Yeah, breaking bonds involves an increase in energy. You have to add energy to tear the particles apart from each other. So the chemical bond energy, and sometimes this is labeled as E chemical, sometimes as E chemical bond, because it is breaking bonds. We are talking about bonds. They're just bonds inside a molecule rather than bonds from one molecule to another molecule. So chemical bond energy goes up as we break apart the reagents. But they don't just stay apart. We don't just shred the X fuel molecules and we don't shred the oxygen molecules and leave them as individual atoms. What happens to those shredded atoms?
They form other bonds?
Yeah, they form new bonds to create the products. And if we're forming bonds, what happens to the bond energy?
Bond energy decreases?
Yeah, the chemical bond energy decreases. And whether a reaction gains energy or loses energy overall depends on which one of these is larger. In some reactions, you have to add lots of energy to break apart the bonds of the reagents, and you decrease the energy a little bit to form bonds of the products. So in that case, you'd have to add more energy than you get out of it, which wouldn't make it very useful as a fuel, of course. But for anything we can use as a fuel, it's useful because you add a little bit of energy to break the original bonds, and then you get even more energy out of it as they form into new bonds. The idea is that the final products are more stable. They're lower energy than the original reagents. So by transitioning from this form to this form, the chemical bonds are transitioning to a lower energy state, and the excess energy leaves the system, presumably as heat. Or in this case, that heat is used to warm up and melt the ice. And so we're going to need some more information here. We're going to need to know, either we're going to need to know how much energy this increases by as we break the bonds, and how much energy this decreases by when we form new bonds. Or maybe we're just given the total amount of energy change for the whole process. So let's say that's the given information. Let's say we already know that combustion of 1 mole of fuel X involves gaining a certain amount of energy. And let's say this is, let's say 1100 kilojoules per mole. And it's usually given in kilojoules per mole in terms of how much energy you get from combusting exactly 1 mole. Or sometimes kilojoules per kilogram, but chemistry usually uses moles instead of kilograms. So this is, you could think of this as our usual delta E bond formula. In this case, we're dealing with chemical bonds, but it still uses the same formula. Delta N, how many moles change phase, times delta H per mole. And we should probably specify per mole of X. Because it's not about moles of oxygen or whatever other reagent, it's about moles of the specified reagent. So each mole of X, when combined with enough oxygen, will combust to release this much energy. And that's really the balance of how much energy it takes to break these apart versus how much energy is released when they form new bonds. So this would be the total delta H for the entire reaction. Any questions on that so far?
Sorry, what was that last bit you were talking about? What is the total?
That we're treating the delta H mole here is the total delta H for the entire combustion process.
Mm-hmm.
Sometimes the information given might be something like, it takes this much energy to break apart X, and it takes this much energy to break apart O2, and you get back this much energy by forming XO2.
Mm-hmm.
Or in this case, perhaps it's just given as, this is the total delta H for the entire reaction shown here. So performing this reaction with exactly 1 mole of X results in releasing this much energy.
Okay, so wouldn't that be a negative sign then, because it's releasing energy?
Sometimes it's written with a negative sign, sometimes it's just written as an absolute value.
Okay.
So really we should probably write this as absolute value of the chemical bond energy equals absolute value of delta N delta H. And we can fill in the positive or negative sign manually. For physical bond energy, if we're talking about changes in phase, whether it's solid, liquid, or gas, you can always get the correct positive versus negative sign by just making sure you use mass of the higher energy state. For chemical bond energy, it's not as consistent as that, though. You got to be very careful about whether it's an increase or decrease in energy. But let's see if we can set up a energy interaction diagram. What types of energy are changing here? We're burning the fuel, burning fuel X, so that's certainly going to involve a change in
bond energy. Right?
Yeah. And I'm going to label that E chemical bond just to be clear that it's talking about chemical changes rather than a phase change. So you've got the E chemical bond of combustion of X and oxygen. And during this combustion overall, is the chemical bond energy increasing or decreasing?
Increasing.
So you have to put energy into it to make it happen?
Yes.
Well, if we got to put energy into it, that doesn't make it very useful as
Wouldn't the overall change in energy be a decrease?
Yeah, we should expect the overall chemical energy to decrease. You do certainly have to put some energy in to spark it, an activation energy to get the reaction going in the first place. But the idea is you put a little bit of energy in to make these molecules combust. As they combust, it releases even more energy, which makes the next molecules start to combust, which releases even more energy, and you get this spreading chain reaction. The whole tank of fuel burns pretty quickly, and all that excess heat leaves the system, or in this case, transfers to the other part of the system and warms up the ice. So we should expect for any fuel, anything where you're burning something, you're using a chemical reaction to power something else, the chemical bond energy is decreasing. These chemicals overall are losing chemical energy and something else is gaining energy.
I have a quick question. So I guess like in a chemical reaction where bonds are forming, will the overall change in energy always be a decrease?
It depends on how it balances out. Like in most chemical reactions, you're breaking bonds and forming bonds.
Right.
We're breaking up the bonds in the reagents and forming new bonds in the products. So as you're breaking bonds, that involves an increase in bond energy. As you're forming new bonds, that involves a decrease in bond energy. So whether the overall change is an increase or a decrease really depends on how those two changes balance out, the positive change and the negative change.
Yeah. Okay.
And generally for any combustion process, anything you're using as fuel, you should expect the total chemical energy to decrease because you need that to decrease so you can power something else increasing.
Got it. Okay.
Which
After,
also ties into the idea of exothermal or exothermic versus endothermic reactions.
Got it. Thank you.
Any other questions on that so far?
after this example, is there a way you could like run us through a combustion reaction and show us an example of when maybe like the chemical bond energy isn't decreasing?
That would basically be something where it doesn't burn on its own, like where you have to constantly apply heat to make it happen.
Oh, okay.
And that would be a situation where breaking the bonds involves a very large increase in energy, and forming new bonds involves a smaller decrease in energy.
And those values would be given to you?
Yeah, presumably either you'd be given values of delta H for each one individually, breaking versus forming bonds, or in this case, you just got delta H for the entire reaction.
Oh, okay, thank you.
And if you did have values for each one individually instead, you take number of moles of this reagent times delta H for that one, combine it with number of moles of the other reagent times delta H for that reagent, and also likewise number of moles of any products times delta H is associated with those.
Oh,
Assign
okay.
positives and negatives based on whether that type of bond is gaining or losing energy, forming versus breaking bonds, and combine all those together to get the total delta H for the entire system, or the entire reagent. Sorry,
Okay.
entire reaction.
That makes sense, thank you.
But in this case, we're assuming we've already got a number for the whole reaction. And that's per mole of the fuel. So we're decreasing the chemical bond energy because this combustion is giving off energy. And where does that energy go? What are we using this reaction to power?
Melting of the ice.
Yeah, we want to melt the ice. The thing is, the ice can't melt yet until it reaches what temperature?
0 degrees Celsius.
Yeah, so let's take a look at a quick three-phase diagram for the ice. We know the ice starts off at -10. So as it gains energy, what's the first type of energy it's going to be gaining?
Thermal.
Yeah, you start off by gaining thermal energy. And the thing is, we don't know yet whether it completes that process. We've got several possibilities here. Maybe the fuel can only cause it to warm up a little bit, not even to 0. Or maybe the fuel causes it to warm up all the way to 0 and partly melt. Or maybe it warms up to 0 and completely melts and the liquid starts to warm up. Maybe the liquid even warms up all the way to 100 and starts boiling. We don't know. So how can we figure that out? If we don't even know which processes are going to finish happening here, how can we find out which ones actually finish?
We would calculate how much it would take to melt to get the ice to 0 degrees Celsius, and then compare that to the energy given off from the bond energy from the chemical.
Yeah, that sounds good. Let's figure out how much energy this would actually take, because it's possible that it maybe gets up to 0. Let's figure out how much energy that is. So we could say, what if the ice reaches 0 degrees Celsius? That's going to be a change in thermal energy. And what formula could we use for that?
Mass times specific heat times delta T.
Sounds good. We'll use our usual MC delta T. We've got 3 kilograms of ice. And we can look up the specific heat on a data table. Oh, and by the way, this data table I've been using, it looks like it's available on the Physics 7A Canvas page. So if you go to Physics 7A Canvas page, and there should be a section of all the FNT documents. At the bottom of that, there should be a document that's just a data table of all these values. So download that if you can find it. It's a very useful reference. So we've got C for solid water. Specific heat looks like 2.05 kilojoules per kilogram Kelvin. And we're assuming it changes temperature by how much?
Is it 10 degrees?
Yeah, it's going from -10. We're assuming all the way up to 0, or just checking what if it goes all the way up to 0. So that's an increase of 10. And since it's a change, Celsius and Kelvin are identical. So we say it's increasing temperature by 10 Kelvin. In terms of the units, kelvins and kelvins cancels out, kilograms and kilograms cancel out. 3 times 2.05 would be 6.15, times 10 would be 61.5. So it looks like warming up the ice all the way to 0 degrees takes 61.5 kilojoules. Now we want to compare that to how much energy can the fuel release as it is burned. So let's try that. Fuel combustion. In this case, there isn't really a what if involved. We're assuming we're burning all 10 moles. So we're burning all 10 moles, that's a change in chemical energy. We can use delta N, delta H. And how many moles are we dealing with here?
Ten moles?
Yeah, we've got 10 moles of X. So 10 moles of chemical X. And then we can multiply that by delta H per mole, 1100 kilojoules. Make some more space here. 10 moles of X multiplied by 1100 kilojoules per mole of X. Moles of X cancel out and we get 11,000 kilojoules. And formally that should be negative 11,000 kilojoules because this is a decrease in chemical bond energy. But we really just need to compare the absolute values anyway. We have 11,000 kilojoules of energy available from the fuel. That's way more than enough to bring the ice up to 0. So we can be absolutely certain that yes, the ice is going to reach 0 degrees. And then what's going to happen next? We've brought the ice up to 0 degrees. There's still plenty of energy left over. So what's going to happen?
I guess we could see if it completes a phase change.
Yeah, because we know it's at least going to start a phase change if it continues gaining more energy. We want to know, is there enough energy available in the fuel to complete the phase change? Going through this transition of bond energy. So for that, we can check another what if. We can say, what if the ice all melts? That'll be another delta E bond, but it'll be a physical bond energy rather than chemical bond energy. So we'll use our usual change in how much there is times heat of melting. And we're assuming we're melting how much ice here?
3 kilograms.
Yeah, we're assuming we're melting all 3 kilograms. And you could look at this in terms of final minus initial as well. Specifically, final minus initial mass of the liquid, since liquid is a higher energy state than solid. We're assuming we end with 3 kilograms of liquid. We started with no liquid, so 3 minus 0. Positive 3 kilograms. And delta H for ice melting. Again, we could look up on the data table. Ice melting, heat of melting, 333.5 kilojoules per kilogram. That's 999, and then an extra 1.5, so 1,000.5 kilojoules. Does the fuel provide enough energy for that to happen?
Yes.
It's like still way more than enough. And note, you got to be careful here. You're not just comparing this value to this value. You're comparing the energy provided by the fuel to all the energy that the ice uses up so far. So you'd be comparing the 11,000 kilojoules available to the 1,062 kilojoules that have been used up so far. But that's still way less than 11,000. We still have plenty of extra energy left over. So what's going to happen next? Now that we've completely melted the ice and we still have plenty of energy left over, what's going to happen?
We could see if the liquid is raised to 100 degrees Celsius.
Yes, the next important transition happens at 100 degrees Celsius. So we need to ask ourselves, what if, or what can the water reach 100 degrees Celsius now that it's liquid? So I'm running out of room here, so I'm just going to make a couple of notes here. So ice warming up requires 61.5 kilojoules. And ice melting costs 1,000.5 kilojoules. And then the next step we're going to look at is
I have a quick question.
water reaches 100.
I have a quick question.
Yeah, go ahead.
I'm a little confused as to where you got the 3 kilograms times 333.5.
This one here?
Yeah. Oh, that's delta M. Okay.
Yeah.
I said delta N, my bad.
All the ice melts, all 3 kilograms.
Right.
And then the 333.5 is delta H melt, the heat of melting for ice melting to water that we just
And that's
looked
from the table, right?
at. Yeah, exactly.
Oh, okay. Okay. Thank you.
That's the, if you can see this, 333.5, there it is. 333.5 is the heat of melting for water.
Okay. Thank you.
So now that we've got those values, any other questions on these two before I erase that part? Okay, so let's check the next step. Next step is the water is going to be warming up, possibly all the way to 100. That's what we want to check. So what if the liquid water, because it's now liquid form, reaches 100 degrees? So we'll get a change in thermal energy. Once again, that'll be our usual formula, MC delta T, mass times specific heat times change in temperature. We now have 3 kilograms still. It's just now liquid. And can we use the same specific heat we had from the previous part?
No, we can't.
Because that was for solid water. Liquid water is going to have different properties. So we look up specific heat of liquid water, and that's 4.18 kilojoules per kilogram Kelvin. We multiply that by what temperature change are we expecting here?
100?
Yeah, because we're going from 0 degrees to 100 degrees. Final minus initial, 100 minus 0 is plus 100. And since it's a delta temperature, we can call it Kelvin, even though the original numbers were in Celsius. Again, the kelvins cancel out, the kilograms cancel out. So we're left with 418 times 3 would be 1,254, I think. So that's how much energy it would cost to raise the liquid water all the way up to the boiling point. So altogether, we've got 1,062 plus 1,254 is about 2,300. Can the fuel provide 2,300 kilojoules?
No, it can't.
No.
We've got 11,000 kilojoules available, right?
Sorry,
Yes,
I
it
have
can.
Yeah.
a
Total
quick
so far.
question.
So it says I thought it was 4.18 kilojoules per kilogram Kelvin. Is it 418?
Oh, it's 4.18, but then we're multiplying by 100 Kelvin because that's the change in temperature.
Okay, cool. Thank you.
So the 4.18 times 100 is 418, and that times 3 would be 1254. So all three of these multiplied together is the energy it takes. If we combine these, our total so far would be, we've got 1200 plus 1000 is 2200, 54 plus 62 is 2316, I think. I might be a little off on that, but that's still way less than the energy available. So the burning of the fuel is providing way more energy than is needed to warm up the ice to 0, melt it, and warm up the liquid to 100. So we know, yes, the water does melt and warm up all the way to 100 and at least start boiling. What's our next big question?
Does it finish vaporizing?
Yeah, so let's figure out if there's enough energy to finish the vaporization process. So we'll say, what if the water all vaporizes? That'll be another bond energy, physical bond energy rather than chemical bond energy. So we'll use our usual amount that changes times how much it costs per amount. And we're assuming how much of it vaporizes.
All of it.
Yeah, so that'll be all 3 kilograms. Is the temperature in the question also supposed to be in Kelvin? The temperature is given in degrees Celsius. But if you're talking about a delta temperature, it doesn't really matter whether it's Celsius or Kelvin. Because if you're taking a delta temperature, how do you calculate delta anything?
Final minus initial.
Yeah, final minus initial. And let's say these are given in Celsius. How do you convert Celsius to Kelvin?
Adding 273.
So if we add 273 to both of these, but we're going to be subtracting them anyway, what happens to those 273s when we subtract?
They cancel out.
Right, those are just going to cancel out anyway. So if you're taking a difference in temperature, they can both be in Celsius or they can both be in Kelvin, and you'll get the exact same result anyway. So as long as you're talking about a difference, Celsius or Kelvin doesn't really matter as long as you're consistent about it. After you subtract the Celsius temperatures, you can just pretend that the difference is in kelvins anyway. Which is why, in this case, for instance, we were raising the temperature by 100 degrees Celsius, but that's equivalent to raising the temperature by 100 Kelvin. And that's really one of the very convenient things about working with deltas. We don't really have to care how much there is, we just have to care how much it changes. Going back to the bond energy, delta H for water boiling. Again, we'd look up on the data table. So water, heat of vaporization, 2,257 kilojoules per kilogram. Again, the kilograms cancel out. 3 times 2257 is 6,771, I think, kilojoules. So that would be the energy required to boil the whole thing. So that's really the largest chunk of energy so far. It takes not as much energy takes only a little bit of energy to warm up the ice, kind of a lot of energy to melt the ice, but still nowhere near as much as is available. About the same amount of energy to warm up the water to 100. Takes a lot more energy to vaporize the water. But even if we combine all these together, what is that going to be? We had 23 something so far, plus another 6,700 something is somewhere in the 9,000. So it's over 9,000 kilojoules. but still not quite enough as, still not quite as much as the energy available. So that means there is enough energy to warm up the ice, melt the ice, warm up the liquid, boil all of it, and then any excess energy is going to accomplish what?
Heating up the vapor.
Yeah, we now have this vapor, this steam, boiled water. That steam is now going to heat up above 100. So, and we know that after it turns to gas, there's going to be no further phase change. It's just going to keep getting hotter and hotter as steam. So at this point, we're done with all of the what ifs. We've finished all the hypotheticals. We know, yes, it is going to warm up. Yes, it's going to melt. Yes, the liquid warms up. Yes, the liquid completely boils. And it's going to warm up further. What's the only unknown left?
The T final.
Yeah, we want to know. We might want to know the final temperature that the steam reaches. The steam is going to get hotter and hotter. We can now figure out how much hotter. We can figure out what is that final temperature. So now that we've checked off all of those what ifs, we can actually put together the rest of the diagram. Can we mark the water boiling? 6,771. We could now even fill in the rest of the energy interaction diagram. We know the water is thermal energy of the ice increasing, bond energy of the ice increasing, thermal energy of the liquid water increasing, thermal energy or bond energy of the liquid water increasing as it boils, and also thermal energy of the steam increasing. But we now know that these are all the changes involved. Nothing else is going to be changing here. And if these are only interacting with each other, if we're able to efficiently use all of the fuel to heat up the H2O, should we treat this as an open system or a closed system?
A closed system?
Yeah, I think we can treat that as a closed system. And that might not be terrifically realistic. Realistically, it's going to be difficult to get all the energy from the fuel into the water. Presumably, we're going to be losing some to heating up the air around it or heating up the container. But let's assume we've got an ideal system where we can use all of the fuel's energy to heat up the water. We can now say, since it's a closed system, what should all of these changes add up to?
0.
Yeah, all these changes add up to 0. We've got a change in chemical energy of the fuel, change in thermal energy of the ice, change in bond energy of the ice melting, change in thermal energy of the liquid water warming up, change in bond energy for the ice boiling, or sorry, for the water boiling, and this change in thermal energy for the steam. All of which have to add up to 0 because the total change in a closed system is 0. Do we not include the bond energies of the X and the O2? This chemical bond energy is really the chemical bond energy change for the entire reaction. So this whole thing, this whole reaction is associated with this delta H value. So we'd only need to include the delta E chemical if we were looking at each reagent and each product individually. But this number, the idea is that this number is for the entire reaction. So we don't need to include the reagents and products separately.
I'm sorry, but
what was that?
can you repeat why? Can you repeat why it was a closed system?
Yeah, we're assuming it's a closed system because we're assuming that all of the energy that we get from the combustion of the fuel, we're assuming all that energy is directed into the H2O. We're assuming we're not losing any energy to the air around it or to the container or anything like that. So let's assume that this combustion is done in basically in a bomb calorimeter. We're assuming we've got this completely enclosed, thermally isolated system. We're doing the whole thing in a test chamber that's completely insulated. No heat allowed in or out. And so that would presumably be specified in the problem. But generally, if you're not told that there's any heat leaving or entering the system, you can usually assume for simplicity that it is a closed system, unless you know that there's some heat entering or leaving. Or alternatively, if you assume it's a closed system and run the calculations and find that these changes don't add up to zero, that means that it presumably is an open system, that there's some energy being gained or lost somewhere. But in this case, we're assuming we're using all of the energy from the fuel to warm up the ice. Any other questions on that so far? And at this point, we don't actually need to fill in the formulas for these as usual because we've already calculated all of them. We've already calculated when you burn all the fuel, what's the energy change for that? What's the delta E chemical if you're burning all the fuel?
11,000.
That's the 11,000 kilojoules we already calculated. Since we already did that calculation, we don't need to do that again. We can just fill in 11,000 kilojoules. We got to be careful about sign though. Should we treat that as an increase or decrease in chemical energy?
Decrease.
Yeah, the chemical energy overall is decreasing. If it was increasing, we wouldn't be using it as a fuel. So that should be treated as negative 11,000. And likewise, we don't really even need to fill in formulas for the ice melting, the ice warming up. We already found out from previous calculations to warm up the ice takes exactly 61.5 kilojoules. So we can just fill in those values we already have. 61.5 kilojoules for the ice warming up. And then for the ice melting, we already found it takes 1,000.5 kilojoules. And for the water warming up, we already found that takes 1,254 kilojoules. And we already found that for the water boiling, it takes 6,771 kilojoules. And by the way, all of these, we can fill in those numbers specifically because we know that that process actually does happen. If we had found, for instance, that there wasn't enough energy to completely boil the water, we couldn't use this number because it didn't happen. We're only using 6,771 here instead of a formula because we found that the water really does completely boil. So we can actually use that number. The only unknown left is this delta E thermal for the steam. So we have this unknown plus, and what formula could be used for delta E thermal of the steam?
Mass times specific heat for steam and delta T.
Sounds good. And we can actually fill that in as mass. We're assuming we now have 3 kilograms of steam because it has all turned into steam. Specific heat for steam is 1.866 kilojoules per kilogram Kelvin times an unknown delta temperature, because we don't know how much the steam's temperature is changing. So these terms all have to add up to 0. Any questions on that setup so far? So now let's try adding all these together and see what we get, because we can combine like terms here. We've got negative 11,000 plus positive 61.5 plus positive 1,000.5 plus positive 1,254 plus positive 6,771. So these terms so far combine to negative 1,913 kilojoules. That's the balance. That's the extra leftover energy that we still have available from burning the fuel after we've warmed up the ice, melted it, warmed up the water, boiled it. This is basically telling us how much leftover energy is available for warming up the steam. We can also combine the 3 times 1.866 to get 5 points. I'm just going to round that off to 5.6, 5.598, but let's say 5.6 kilojoules, and the kilograms cancel out. So we get kilojoules per Kelvin times delta temperature. And what else do we need to do to solve for temperature here?
To T final minus T initial. So
Yeah, we could fill in T final minus T initial here. T final is unknown. But what's the initial temperature for the steam?
100 degrees Celsius.
Yeah. Because even though the original ice started off at -20, we already took care of all the temperature changes up to 100. The steam started at 100 degrees. So how do we isolate T final here? Algebraically, what's our next step?
You multiply 5.6.
You could distribute the 5.6 to both of these terms, but I think it might actually be easier to leave this as is for now and just undo everything that's being done to T final. Like if you think of this in terms of order of operations, what's the very last step that would be done here?
Well, I guess you could put 1,913 onto the right and then divide that by 5.6.
Yeah, I think that would be a more efficient way to solve it. If we start by adding 1,913 to both sides, and then divide both sides by 5.6 kilojoules per Kelvin. So then we get T final minus 100 degrees Celsius equals about 342. And when we divide those, dividing by kilojoules per kilogram is the same as multiplying by kelvins per kilojoule. So the kilojoules cancel out, we end up with Kelvin. So 342 Kelvin is the change in temperature. But a change is the same whether it's in Kelvin or Celsius. So we can treat this as a change of 342 degrees Celsius. That is 342 degrees above and beyond the starting temperature. Add 100 to both sides and we get the final temperature is 442 degrees Celsius. So it looks like burning 10 moles of fuel is enough to warm up, melt, warm up, vaporize, and warm up further. So we end up with steam at 442 degrees Celsius. Any questions on that?
Do sig figs matter in this case? Yes, right?
Normally, yes. The 7 series usually doesn't emphasize that all that much.
Okay.
I would recommend using sig figs if you can, just to get some more practice with it and make sure you stay accustomed to it. But I don't think the Physics 7 instructors usually worry about it too much.
Okay.
If we did, we certainly would include, for instance, the usual rules. For instance, this, if we only know 3 up to 1 significant figure, we shouldn't be using more than 1 significant figure in the result. So be careful with significant figures, but for most practical purposes in the Physics 7 series, I would assume that 3 kilograms means we know it very precisely. But,
so is this kind of a question that they would ask on a midterm? This kind of question?
Possibly, yeah. I mean, it might be different numbers, of course, different substances, but I would imagine something like this being a useful test problem.
Mm-hmm.
Is checking how you combine these types of energy and being able to predict what types of energy are actually going to be changing if you have this much energy available.
Mm-hmm.
Checking all those hypotheticals, for instance. Any other questions on that?
So to get from 342 Kelvin and then we ended up with the T final as 442 Celsius, it's because adding 100 degrees Celsius is the same as 100 Kelvin.
Yeah, or I guess the other way around, really, that we're starting at 100 degrees Celsius. The 342 is the change in temperature. So we're increasing the temperature 342 kelvins beyond what it was to start with. But raising the temperature by 342 Kelvin and raising the temperature by 342 degrees Celsius is the same change.
Okay,
So the
thank you.
steam was at 100 degrees. There's enough energy available to raise the temperature by 342 degrees above that. So 342 degrees above 100 degrees becomes 442 degrees as the new final temperature.
Okay, thank you.
You could also do this by converting everything to Kelvin in the first place, but you don't need to. Since the changes are Kelvin or Celsius equivalent, you can just treat everything as if it's in Celsius. Any other questions on that? And if you
I have a question.
Yeah, go ahead.
Okay. So for the final temperature that we solved for, which is 442 degrees Celsius, so is that like the final temperature needed to convert steam from the whole compound? Is that what it
I would
means?
say that's more the final temperature that the steam reaches after all the fuel finishes burning.
Okay, got
So
it.
presumably this process doesn't happen all at once. It's a gradual process over some period of time. So as you burn the fuel, each one of these happens in that sequence. First the ice warms up, then the ice melts, then the water warms up, then the water boils, and then the steam continues to warm up. And by the time you run out of fuel, the steam has reached this final temperature.
Got it. Okay, thank you.
And if you want to get some more general practice on just thermal energy and bond energy and how they interact and checking all these what if hypotheticals, I've got a worksheet on mathandcheese.org. If you go to math.andcheese.org/P7A, let me post the link here. There should be a worksheet there with just a bunch of more practice problems on thermal energy and bond energy. So give that a try if you want to get some more practice. Feel free to bring that into office hours if you need some help with it. And we will continue with kinetic energy and potential energy next time. See you then.
Thank you.
You're welcome.